All right, so this is the video for our chapter one lecture. Um, chapter one is very introductory, not just to chemistry, but to the textbook itself and like the process of learning chemistry. So we're going to go over a lot of different intro topics, okay? But we need to know them all because they're all important to be able to build on it later when we're tackling like things that are a little bit tougher. All right, so the learning goal for this part of the chapter is to define the term chemistry and identify what chemicals are, which is a pretty important part of chemistry. When we're talking about chemistry in general, we're talking about the idea that we're going to study the composition, structure, and properties of the things that are around us. Okay, reactions that matter is undergoing. Literally everything that we experience in our daily lives is a result of chemistry. It's just that we don't always call it that, even when we're watching it happen, even something like this, right? It's just a chemical reaction, but it's something that we're sort of used to. When we use the term matter, we're talking about the name for what makes up everything. So the definition of matter is that it's anything that has mass and occupies space, right? So anything that you can like see, anything that you can take like a mass measurement of, all of that's matter. So everything that we interact with in the world around us, that's all considered matter. What's not considered matter are things like energy, like like light, for example. That's not going to have mass. That's not going to occupy space, and that's how you can tell the difference between what is matter and what's not matter. Now, when we use the word chemicals, we're talking about a really broad name for substances that have the same composition and properties wherever you find them. Okay. Um, so yeah, there are chemicals that are in our everyday compounds, right? Things like toothpaste, for example, is a combination of a lot of different chemicals. Um, but chemicals are in everything that like that we're working with, that we're eating on a daily basis. This is a very mouth care heavy list of different chemicals. It's all the stuff that's in toothpaste and how they kind of come together to create a good toothpaste. So you can have some chemicals whose main purpose is to like remove plaque. You can have others like the titanium dioxide. That's what's going to give the toothpaste its color. The sodium fluorophosphate prevents the formation of cavities. So like it all comes together to like make up the thing that you use that's toothpaste. All right, let's look at the learning check here. Which of the following contains chemicals? Um, Pretty much all matter contains chemicals. So if it's matter, it's got chemicals. And if it's not matter, it's not going to have chemicals. So if we look through these answer choices, I'll put up the answer slide so we can talk through what's next to them. Sunlight on this list is this is the only option on this list that wasn't a type of matter. And if it's not matter, then it's not going to contain chemicals. But even things that are natural or that what we would classify in our heads, I think, as natural, things like fruit that haven't necessarily, like they haven't gone through a factory or anything. You just grow fruit. But fruit still contains its own type of chemicals. Okay, even though it was grown somewhere. Milk is another type of matter, so it's also going to contain chemicals, and then breakfast cereal as well. Right? So if it's a type of matter, it's going to contain chemicals. Now let's talk a little bit about the scientific method. This is the process that we're going to use to sort of think through the different problems that we run into, not just in lab, but in general. You can use the scientific method to kind of work through any any question that you're having if you're trying to like figure out why something is doing what it's doing. But it's important to look at the scientific method because it's how a lot of our scientific laws were created. It's also very similar to the process that we're going to apply when we're in lab and we're going through our experiments. Even if we don't call it, like, even if we don't outline each step of the scientific method, that's still going to be what we're doing when we're sitting there and we're going through our experiments. So the scientific method is going to be just a general set of principles that's going to help us go through and think about things scientifically. And you can follow the same 4 sets of steps when you're approaching the scientific method. The first one, the most important one, is that you're going to be making observations, okay, about nature, about what you're seeing, about the things that you observe, right? Observations, it's what you observe. When after many observations and sort of many cycles through you like proving that what you're seeing never changes, observations can then sort of be stated as a law. Laws are scientific laws are they're things that you can rely on. Okay. So a good example that we talked about in class is the law of conservation of mass. That law says that whatever, when you start an experiment, if you measure the masses of the things that you start with, and then you put it through the experiment and you watch the reaction happen, you watch the stuff that you start with change the way they look, right? Maybe you'll see some bubbling or something dissolve or something like that. So all the reaction happens, and then at the end of the reaction, you collect everything that was made, okay? And if you take the mass measurement of that as well, you'll see that the 2 mass values are the same, okay? That wasn't something that, excuse me, that scientist just knew. That's something that one particular scientist tested many, many times and consistently compared the mass of what he started with, the mass of what he ended with, and it was always the same. So that's one of the ways that you can go through and use what you're observing to like create these scientific laws, which then other people can use to predict behavior, right? So like we can use that scientific law and now we know what to expect when we're doing a chemical reaction. The mass of what we start with should equal the mass of what we end with. To get to that point where you're kind of creating these scientific laws, you want to take your observations and you want to create a hypothesis from them. Okay, and a hypothesis is going to be your explanation for what you're seeing. Okay, a hypothesis doesn't necessarily have to be correct, but it's your best explanation for the things that you're looking at. Okay. From the hypothesis, you're going to design an experiment. And that experiment should be created in order to test whether the hypothesis is true or not true. Okay. A good experiment is an experiment that's going to be able to prove or disprove your hypothesis when the experiment is done. Okay. So like it should give you information that's helpful. Sometimes people design experiments and you get to the end of the experiment and it didn't give them an answer to the question that they asked. So when you design an experiment, you want to make sure that you're designing it with that in mind. Like when I get to the end of this experiment, will it answer the question that I'm asking? Will it give me information about my hypothesis, telling me whether it's true or not true? And at the end of your experiment, you'll have enough information to figure out your next step. Okay. If your experiment proved your hypothesis was true, then you can draw a conclusion from that. But if your experiment proved that your hypothesis was false, then you have to go back and rethink your hypothesis and say, okay, well, my first hypothesis was not true. So what else could have caused what I'm observing? Okay. We'll look at a chart in a second and we'll track back through that, but let's just talk through the example that they give here because it's relatable. Suppose you visit a friend in her home and soon after you arrive, you begin to sneeze. And so they're like, what's going on? And then you observe that your friend has a new cat. And so you're like, all right, well, why am I sneezing? Maybe I'm allergic to cats. I've never been around cats before, but maybe I'm allergic to cats. And so you perform experiments to test your hypothesis. So you visit other friends with cats, other friends without cats, and you see whether your sneezing increases or decreases based on where you are. So if you sneeze after you are in other homes that have cats as well, then you can say, all right, well, my experiment of visiting all these cat houses, it leads me to the conclusion that I am allergic to cats. Okay. So it's a very like drawn out example, but you could see how it relates. This is a good chart that you can use to track the scientific method. And it just kind of shows the steps that we talked about. So everything starts with observations, right? And repeated observations over many, many different scenarios will eventually turn into laws. But with these observations, we're going to use those to create our hypothesis, which is our best explanation. And from our hypothesis, we're going to design an experiment, which should test whether our hypothesis is true or not. And if it's true, if our experiment shows that our hypothesis is a good hypothesis, then we can draw a conclusion from that. If our experiment does not show that, then we're going to go back and we're going to rethink our hypothesis. Okay. All right, that slide just says what we just said. All right, so identifying each of the following as an observation, a hypothesis, an experiment, or a conclusion. Okay, so during your gym, for these ones, I would say that anytime I get to a learning check here, while you're using these videos, pause me for a bit and try to answer the question yourself. And then you can go through and check whether you got it or not. So it's a little more interactive, and then you can actually sort of see if you're progressing with what we're covering. So during your visit to the gym, your trainer records that you ran for 25 minutes on a treadmill. Okay. When you're looking to see which of those options applies to this statement, you have to ask yourself, is there any explanation here? Is there any, is there any experiment being created? No. Your trainer is just recording something, right? And recording something, that's a type of observation. So this first one is going to be an observation. Second statement, scientific studies show that exercising lowers blood pressure. And the key word here is, or the key words, scientific studies show. So this shows that this relationship between exercising and lowering blood pressure has been looked at many times. Okay. And if it's been looked at many times, then a conclusion is being drawn, right? It's been studied already. Option C, your doctor thinks that your weight loss is due to increased exercise. And so that word right here, that's going to be our key word to classify this as a hypothesis, okay? Because a hypothesis is your best explanation. So it's what you think. Okay, we'll try this set now. During an assessment in the emergency room, a nurse writes that a patient has a resting pulse of 30 beats per minute. So the important phrase here, right, is a nurse writes. So that's going to be the nurse making an observation. Okay. She's not trying to make an explanation out of anything. She's not designing an experiment. She's just writing down what she sees. Repeated studies show that lowering sodium in a diet leads to a decrease in blood pressure. So again, we have that phrase, repeated studies show. So again, that's going to be linked to a conclusion because we've already had something that's been proven many times. And then statement C, a nurse thinks that an incision from a recent surgery that is red and swollen is infected. So right there. Okay. That's going to be a hypothesis. All right, so let's shift gears here and let's talk about how to tackle studying chemistry and tackle the textbook in general. This section goes through some good ideas for study plans, ways to engage with the material and form good study habits. You could think about these three things like a checklist that you want to go through whenever you're going on to a new chapter. Connecting any new information that you're receiving to the knowledge that you already have, rechecking whatever you've learned to see what you've forgotten and sort of refresh yourself so that it's never too far away, retrieving what you've learned for an exam, right? And I know that when you're taking a class like this, that's on the front of everyone's mind. You want to be able to retrieve that information when you're sitting down for an exam. So some tips to form good study habits for like having a successful experience in a class like this one where you're getting a lot of information that's very new. You got to try to ask yourself questions as you read your textbook. You have to try to self-test as you go. So you can use, like you could ask yourself questions. There's questions that come up in the textbook that you can use as well. You want to study at a regular pace. You don't want to cram right before the test. And you want to be able to take the different topics in your chapter and relate the new information that you're getting back to things that you've already learned. A little bit of a tour of your textbook. You're going to have your periodic table available in the front inside cover of it. The tables will be in the back inside cover. In the chapter themselves, you're going to have three things that are at the beginning of the chapter that you can take a look at. There'll be looking ahead sections, learning goals, and reviews. Then you're going to see in the margins of the text itself, you'll have these icons that pop up. One of them is going to say key math skills. The other is going to say core chemistry skills. These are two things that you know when you see those icons, you have to be good at the things that are noted there because those are things that are important for you to progress in chemistry. Okay. You'll have key terms that are bolded throughout the text. And then you'll have a glossary at the end of the text. Your glossary tells you the definitions of all the bold terms that are in your chapters. And your index tells you where you can find different topics if you're looking for a specific thing. So before you start reading your chapters, you might want to go look at the looking ahead sections, looking at the learning goals and the reviews at the beginning. Excuse me. Because when you look at these sections, like the looking ahead section, you can take that title and rephrase it as a question for yourself and like use that as the thing that you're going to try to answer as you go and you read through the chapter. So you have a goal in mind. You want to make sure that you're not just reading the chapter from start to finish because you're not going to retain that information the same way. Try to take breaks within the chapter itself. So like when you get to one of the engage questions there, like stop and do that question because it breaks up the reading. When you get to a sample problem, like you try to work it through first before you look at their solution. Because then again, it's like you're breaking up the reading, but you're also then trying to apply what you're reading. And then at the end of every chapter, there's practice problems, or at the end of every section, there's practice problems, as well as at the end of the chapter. That gives you more opportunities to try things out. You'll also see that because the textbook we're using is kind of linked to an entry into the medical field specifically. There's a lot of links to, excuse me, health, the environment, and clinical applications of problems. So it's nice to see how we're looking at like real world applications for some of this. You're going to have figures, diagrams, and videos available. Figures and diagrams will be available in the text version as well as the e-text version. But the e-text that's available through Pearson is going to have interactive videos that you can use while you're reading. And sometimes when you are reading the chapter and you're having when you're having problems with a particular topic, it's really nice to go in and have someone like verbally explain it. So uh, you might find those interactive videos like very helpful. And then at the end of the chapter, there's going to be certain things that are put together to act like a study aid, or at least they're there to help you design your own study aid. So there's going to be a review of the chapter that provides a summary of everything that was covered. There'll also be a concept map, which shows how all the things are connected to one another. The key terms are again listed. Those are all the bold words that you picked up throughout the chapter. And they have their definitions next to them, which is helpful. A list of your key math skills and your core chemistry skills. And then some additional information, including the concepts, the practice problems, and even challenge problems if you wanted to go a step further, which is all going to just help you kind of work with the material you've just learned a little bit more, like give you a little bit more practice with it, a little more understanding of it. So once you get done with the reading, this is a really good place to end and to like do a few of these problems to like really cement that knowledge. You also want to make a study plan, okay? And the suggestions here, it's not like you have to do all of these. I mean, if you did, that'd be wonderful, but these are just the types of things that are going to be helpful to you. Reading the chapters before class, the chapters are all online, so you can read them all before you come to class. If you know we're going to study chapter 3, for example, read through chapter 3 before you come to class so that the things that you're hearing in lecture aren't completely new to you. It makes it a lot easier to absorb the material when it's not the first time that you've heard it. For sure, going to class is going to be critical to your success. Reviewing the learning goals is helpful because then the things that you're learning are not going to be a surprise. You'll be expecting the next thing. Keeping a problem notebook. You could think about a problem notebook as like a few things. If you have one designated notebook for this class, right? You can have one place where you're writing out all the practice problems, but it's also a notebook where you can write down the things that you're not understanding as you're studying. So like when you want to meet with me, when you want to meet with one of the tutors or something like that, you have a list of things. And you're like, these are the things that I'm having trouble with when I was working through these problems. Okay. So it's really good to have one place where you have all of the problems that you're working out, because you can see the progression of the material. It's going to go from things that were a lot not easier, but just a lot less complicated at the beginning. And we're going to move into stuff that seems more complicated. So it's nice to have one place where you can watch that progression happen. But it's also nice to have one place where you're keeping, like maybe at the back of your notebook, you can have like a list of things that you want to, questions you have, or things you want to go over again. Because that's going to help you direct your studying for your exam. Definitely reading the textbook in general and working through practice problems is incredibly important for the studying process. You can use the engage questions to guide your reading, and then, practice. It's also a really good idea to study different topics at the same time because it helps you connect them. I know a lot of people get like hyper focused in like one particular area, but if you do manage to like look at a few different things, you're able to start pulling things together and make it a little more cohesive. So you're like, all right, I understand the overall goal that we're trying to get to here, and I don't just understand this one specific thing. People also have a lot of success with study groups. So within the class itself, if you can find some people that that you can connect with, and then you can just, even if you're jumping online or something like that before an exam and like testing each other on things, asking each other questions. One of the best ways that you can be sure that you understand the material is if you're able to explain it to someone else. So one really good method to use in a study group is to like take turns explaining a topic to the other people in the group, and not just have one person do it, but like have everyone take a turn doing a different topic so that you're really understanding it then. Okay. And if you can't explain it, and it's fine if you can't explain it on the first try, but if you can't explain it, then you're like, all right, well, I'm going to have to work on that one a little bit more. Right. And that's what you want to do while you're studying. Use office hours, use the tutoring center that the college has, review the math skills and the core chemistry skills. If review sessions are offered and if review material is offered, make sure that you're using that. And study a little bit at a time, right? Spread it out. Make time for this class every day. I know that everyone's busy. I understand that. It doesn't have to be a lot of time every day, but it's a new subject, such a new subject that you want to be able to think about it a little bit every day so you never are able to forget anything. Okay. If you're only studying it once or twice a week, then it's going to be easier to forget things in the intervals, right? You'll even see in class that when we go from Thursday back to Tuesday, the Tuesdays are always a little bit harder to get back into because you've had all those days off. But when you go from Tuesday to Thursday, you get to Thursday and it's a lot easier to recall the stuff that we've done. So this is a funny question we can look at. I think that the correct answers stand out pretty easily. Which of the following activities should be included in your study plan for learning chemistry? Definitely not skipping class. But yes, any of these other ones. Forming a study group, great. Keeping a problem notebook, great. Working on practice problems as you read each section, absolutely. Hopefully all three of those, B, C, and D. And hopefully we're not skipping class at this point. All right, so let's look at some of the key math skills. For chemistry, this is going to seem a little bit non-chemistry related, but the fact of the matter is that you need to have a good grasp of some of your earlier math skills to be able to apply them to the math that we have to do in the class. So we're going to look through some of this stuff. For starters, identifying place values. Place values are the names of the actual numerical value that each number has. Okay. So you see them listed here. We're going to need to know from the thousands value to the thousandths value. Okay. You'll notice in the numbers that appear to the left of your decimal place, there's no change to the spelling of these words, right? This is 2000. This is the thousands place. This is 500. This is the hundreds place, right? This one would represent, the tens place. And the 8 would represent the ones place, right? So we're describing the value that each of these numbers would have. When you move to the right side of your decimal, the ending of the word is going to switch to this THS ending. Okay, so the 6 in this case, this is right before the decimal. This is your ones place. And as soon as you move past the decimal place, the first place you encounter is the tenths place. Okay, and after the tenths place is the hundredths place. Me trying to say this while you can't see my face. I'm trying to make the ending real dramatic. And after the hundredths place is the thousandths place. But we do want to be able to identify those places, okay? Because it's going to make it easier when we're talking about specific numbers, when we're identifying which number is our last significant figure, things like that, if we can point to a specific place. So what is the place value for the underlying digit in 35.679? We know that this is our ones place here. This is the tenths place. And so this is going to be the hundredths place. Okay, so this one right here, choice D. A bullet found at a crime scene has a mass of 15.24 grams. What are the place values for each of the digits in the mass of the bullet? Right, so when you look at that number, you can always start at the decimal if that makes it easier. And to the left of the decimal, this is always going to be the ones. And then after that is going to be the tens, right? And then hundreds and then thousands. So this is our ones place. This is our tens place. To the right of the decimal, this is our tenths place. And after that, to the right of the tenths place is the hundredths place. Okay. Let's look at our number line and our positive and negative numbers here. Positive numbers are going to be any value that is greater than 0. Those are going to get a positive sign that we don't actually write in, but we understand that it's there. Negative numbers are going to be any values that are less than 0, and those are going to have a negative sign in front of them. And if you think about it in terms of a number line, everything to the right of the 0 here is positive. Everything to the left is going to be negative. So we can use our number line to kind of determine what the absolute value of particular distances are. Okay, when we say the term absolute value, we're talking about how far a number is from 0 without considering the direction from 0, or how many spaces are between two values without worrying about their signs. Okay. So what do we mean by that? If we're looking at this question here on a number line, how far apart are -2 and 7? Let's just try to draw in something here. So our -2 is going to be here, right? And our 7 is going to be here. And so what we're worried about are how many actual spaces are between those values, not whether the -2, is negative and the 7 is positive. So if we count those spaces, we have like 1 space, 2, 3, 4, 5, 6, 7, 8, 9 spaces between them. And so you could think about the distance between -2 and 7 as like 9 spaces or 9 units. And that's going to be an absolute value. Okay. So let's think about these questions. On a number line, which the following is the greatest distance? So if we'll look at each one of these and try to track like how many units are between these values that they're giving us. So our first one is -3 and 0. So if we start at -3, we're like, okay, there's 1, 2, 3 spaces between them. Okay. Apologize for I'm going to write this out with my mouse, so it's going to look dumb, but you get it. The distance between -1 and 2, all right, if we start at -1, we're going to have 1, 2, 3 spaces between our -1 and our 2. The distance between -2 and 2. Okay, so I'll go underneath for this one. So if we start at -2, we go 1, 2, 3, 4 spaces. And then the distance between 5 and 8. So if we start at 5, 5 to 6, 6 to 7, 7 to 8. Right? So in this case, the greatest distance is being covered by choice C, right? That distance between -2 and +2. I'll just get rid of those guys. Boop, boop. Or else they stay on the next slide. Okay. I didn't want to just put up the answers without showing how we got them. So we'll try a different version of this question. If we're looking at, we want to find the following values, and then we're going to use those values to figure out what this distance is, or what this number is. So if we're looking at the distance between -2 and 5 on the number line, and we're going to start at -2, and we're going to go, all right, there's 1 space, 2 space, 3, 4, 5, 6. All right, there's 7 spaces. My very good mouse work there. 7 spaces. The distance between -1 and 3. All right, I'm starting at -1, and so I'm going to go 1, 2, 3, 4 spaces. Okay, and so now when I'm doing what's A minus B, I'm just going to subtract those. Okay. It's a second to do this. All right. On your number line in general, and number lines are just useful to help you track positive and negative numbers. If it ever gets confusing, you don't have to use a number line to do your calculations, but if you're finding the switching signs troubling, sometimes it's easier to look at the number line and just watch the numbers move left to right. Your number lines are going to be spread equally in both directions, right? And just, they kind of go on forever. This goes on forever to the right, and the negative side goes on forever to the left. There's no end to our numbers. But we can use our number line to help us out visually with some of the math that we need to do. So let's think about adding numbers, adding and subtracting with different types of signs. Okay. When we're adding numbers together and they have the same sign, that means that those numbers are going to be going in the same direction on the number line. So if you add +5 and +5 together, you'd start at +5 on the number line, and you'd go 5 more units in the positive direction, which is the right direction, or towards the right. When you add numbers that have the same sign, you're always going to end up with the same sign that you started with. So if you add 2 positive numbers together, they'll end up with a positive answer. If you add 2 negative numbers together, you'll end up with the negative answer. The sign does not change, to be clear. So when you're adding numbers that have the same sign, your answer will have the same sign as the numbers that you were adding. A shorthand way that you can do this, when you're adding numbers that have the same sign, you can add the numbers by themselves without incorporating the signs. And then once you're finished, just assign whatever the sign was that you started with. So like if you're adding +5 and +5, you could just be like, oh, 5 and 5 is 10, and I'm going to put a positive in front of it. If you're adding -5 and -5 together, you could do 5 and 5 is 10, and then put a negative sign in front of it. When you're adding numbers that have different signs, there's a few ways that you could think about it. We had a good summary in class for it, actually. You're gonna basically be finding the difference between the 2 values that you're starting with. Okay, and you'll notice here that when you're adding -5 and +7 together, the difference between these 2 numbers is 2, right? Because our positive value is the larger value out of these 2 numbers, our answer will also be positive. Okay. If we look at a slightly modified example down here, -7 plus +5. Okay. The difference between 7 and 5 is still 2. But in this case, the -7, the negative number is bigger. And so the sign in front of my answer is going to be the same sign as whichever number was larger, right? So the 7 was negative in the second example, so my answer was negative. The 7 was positive in my first example, so my answer was positive. So I feel like that might be an easy way to tackle those types of questions. Okay. You can always find the difference between the numbers and then assign the same sign as whichever value was your bigger value when you were starting the calculation. These are just some examples here. So two numbers with the same sign, right? +3 and +4, we end up with +7. When we have -3 plus -4, we end up with -7. And when we have numbers with different signs, 12 plus -15, we look at the difference between these two numbers. So the difference between 12 and 15 is 3. And then we give it the same sign as whichever number was larger. Okay. For our subtraction, when we subtract numbers that have the same sign, that means that we're subtracting values that go in the same direction on the number line. It's very similar to what we were talking about with the addition. So when we use the number line, we can start at the first value, then we can add whatever number of negative units, which means we'd be going to the left of our starting value. Okay. So if we're doing like -5 minus 5, we'd start at the -5 and we'd count 5 to the left and we'd end up with -10. Subtracting numbers with different signs means that we have to find the difference in those values again. Okay. Using a number line would let you start at the first value and then just move further left. Okay. So if you like start at +7 on the number line and then you move 5 spaces to the left, you'll end up at +2, which is the answer. So here's some of the variations that you can see. If we start at +12 and we move 5 to the left, 1, 2, 3, 4, 5, we end up at 7. Okay. Where it gets interesting is when you have double negatives right here. Double negatives in math, they work the same way as like double negatives in language, where they cancel each other out. Okay. If you're gonna subtract something that's negative, you're pretty much reversing the direction of this sign. So instead of doing 12 minus 5, which is what we did up here, right? We started at 12 and then we took away +5. If I start at 12 and I want to take away -5, well, I have to go in the opposite direction. Now, if I'm taking away negatives, that means I'm making it more positive because I'm removing negatives, right? Do you understand that? Like removing a negative is the same thing as making something positive. So 12 minus -5 is like saying you're adding 5 to 12. So that's why we end up going in the right direction by 5. Okay. Because when you remove a negative, you make something positive. All right. So try to think about that logically when you're trying to reason it out. When you remove a positive, you're making something more negative, which is why when you have the minus and the plus signs here, that's why you just go in the same negative direction on your number line. So if we start at -12 and we want to subtract +5, we want to remove 5 positives. So 1, 2, 3, 4, 5. But if I start at -12 and I want to remove 5 negatives, that means that I have to go in the positive direction. 1, 2, 3, 4, 5. All right. And when you're multiplying and dividing, this is a good rule of thumb to refer to when you're trying to figure out what the ending sign should be of your answer. When you are multiplying and dividing things that have the same sign, your answer is always going to be positive, right? So if you're multiplying two positives, it's positive. If you're multiplying two negatives, it's positive. If you're dividing two positives, it's positive. You're dividing two negatives, it's positive. Right? When you have that the same sign for both, you have a positive answer. When you have opposite signs, right? So negative, positive, or positive, negative, then your answer is always a negative. Even if you're multiplying more than two things, if you have one sign that's different, then your answer is going to be negative. Same thing is true with division. Negative divided by a positive is negative. Positive divided by a negative is negative. Okay. And we can look at these answers. Ignore this one though. This one's wrong. Hold on, I'm gonna just draw a little positive right here. Bloop. There. Now it's right. When two positive numbers or two negative numbers are multiplied or divided, the answer is going to be positive. You don't have to write the positive sign in there. When there is no sign included, then everyone understands that you mean it's positive. So 2 times 3, positive 6. Negative 2 times negative 3, positive 6. Okay. 6 divided by 3, positive 2. Negative 6 divided by negative 3, positive 2. And then when we have opposite signs, this is when we end up with our negative answers, right? So we have a negative 3 times our positive 2, negative 6. So as long as you have, one sign that's different than the other, your answer is going to end up being negative. That's why we had to fix this one. All right. For the calculator operations, like I said in class, the easiest way that you're going to be able to figure out your calculator is to have it available as soon as possible in the classroom so that you're working with it. You're not able to use your phones or any electronics other than your scientific calculator on exam day. So you want to make sure that you have this early so you understand what all the functions are. Okay. You're just like a cheap, like a $10 scientific calculator. Something that has the log function in it for when we get to the later chapters would be the best idea. And then we can work on putting things in not just these operations with the multiplication, division, subtraction, but we can also work on putting things in terms of like scientific notation, which we'll talk about in a little bit, putting in exponents. All right. But the sooner you have that calculator, the more familiar you'll be with it. And then it'll be easier to use it on your exam because sometimes when you're using something brand new on test day, there's a learning curve to that. All right, let's look at some percentages. To figure out percentages overall, and again, this will link to what we talk about in later chapters. To take a percentage, we're looking at the part of something, so like a subset or an individual section of something, dividing it by the total value of that thing, and then multiplying it by 100. Okay. So in this first example, we're saying that a person has 32 books total, and 8 of those books are chemistry books. So if you wanted to know what percentage of their personal library was chemistry books, you would take the 8 chemistry books, which is the part, and divide it by the 32 total books, which would be the whole, and then multiply it by 100. So 25% of those persons' books are chemistry books. Another example here, if there's a bin and there are 100 different multicolored balls in there, and we wanted to know what percentage of the balls were red. Okay, we count through and we find out there's 5 red balls in all of the balls that are in there. Sorry. Then we can find the percentage of the red ones by taking the 5 red ones, which would be our part, dividing it by the 100 balls total, which would be the whole, and multiplying it by 100. So 5% of the balls would be red. Okay, we're going to work through this example. A bullet found at a crime scene may be used as evidence in a trial if the percentage of metals is a match to the composition of the metals in a bullet from the suspect's ammunition. Sarah's analysis of the bullet showed that it contains 13.9 grams of lead, 0.3 grams of tin, and 0.9 grams of antimony. What's the percentage of each metal in the bullet? And we'll express our answers to the ones place. So let me just write down this information and then we'll switch over to the board. Lead, tin, and antimony. And again, this would be a good spot where you could pause it, try it out on your own now, and then compare it to what I do. Okay, so lead, let's get used to the element symbols here. The symbol for that is PB. And we've got 13.9 grams. Tin, symbol is SN. And we've got 0.3 grams. And antimony has the symbol SB and 0.9 grams. Okay. So now to find the mass percent, we're looking for part over the whole. All right. So the first thing that we have to do is we have to figure out what the total mass is here. So we're going to add all these together. Okay. So we've got a total mass of 15.1 grams total. Okay. Now to find our percentage of each, we're going to take the individual mass of that element, divide it by the total mass, and multiply it by 100. And we're going to round it to the ones place because that's what they asked for in this calculation. Okay. And then we'll do the same thing for the tin. So the 0.3 grams for the tin divided by the 15.1 grams total times 100. And we get 1.986. So we're going to round that up to 2. So it's in the ones place. And then for our antimony, we're going to do 0.9 grams divided by 15.1 grams times 100. And we get 5.96. So we'll round that up to 6%. Okay. So those are our percentages for the crime scene bullet. Okay. Now the next question that they ask us here, let me put this back up real quick just so we can look at the wording. They ask us, all right, so we have a bullet that was seized from the suspect's ammunition, and they give us the composition of that suspect ammunition. Okay, so 11.6 grams of lead, 0.5 grams of tin, 0.4 grams of antimony. So now we have two things we need to do. We need to calculate the percentage of each metal in that bullet, and then we have to compare the percentages to determine whether the bullet that was removed from the suspect's ammunition could be evidence that the suspect actually committed the crime mentioned. Okay. So go back to the board. So we'll do this. This is the crime scene. And we'll do the suspect over here. Okay, so for our lead, the suspect ammunition had 11.6 grams. For the tin, the suspect ammunition was 0.5 grams. And then our antimony suspect ammunition was 0.4 grams. Okay, so again, we'll add those together, figure out what our total is. So we've got 12.5 grams total. And now we're going to go through and find our percentages so that we can compare them. Okay. So our lead is going to be 11.6 grams over 12.5 grams times 100. And we get 92.8, which will, again, we're rounding it to the ones place. So it's going to be 93%. It's a little different. For our tin, we're going to get 0.5 grams divided by 12.5 grams times 100. And we're going to get 4%. That's a little more different. And then for our antimony, we're going to have 0.4 grams divided by 12.5 grams. And we end up with 3%. Okay, so now we can analyze these, right? The 92 versus the 93, maybe that's an acceptable amount of error, maybe. But 2 to 4, that's a pretty significant difference. And 6 and 3, that's also a very large difference in terms of percentage. So looking at these two things, you would say that there'd be enough difference here that this suspect's ammunition did not match the ammunition that was at the crime scene. All right, let's take another look. Well, let's take a look at the next part of this now. So we're going to look at solving equations. We're going to be looking at a lot of different equations over the course of the semester, and we want to be comfortable solving for unknown variables. Okay, there's always going to be an unknown variable somewhere in the equation that we need to solve. And so we want to be able to manipulate those equations so that we can get to the piece of information that we're focused on. So we're actually leaving this up here for a second. I'll write this down, but then we'll talk through the steps that they're doing here. All right, so for this example, they're asking us to solve for x. X is our unknown variable here, okay? And when you're solving an equation algebraically, you want to try to place the variables on one side and the non-variables on the other side, right? That's your goal. They say separate the terms. You want to place all like terms on the same side. And when they say that phrase like terms, they're talking about things that have variables attached to them and then things that don't, right? When you're moving things around in an equation, the only way you can move something from one side of the equation to the other side is by doing the opposite math operation to it. So if something's being added on this side, then you have to subtract it from both sides to move it over. If something's being multiplied on one side, then you have to divide it on both sides to move it over. Okay? So here we want to get the 8 on the side with the 14. So we're going to do the opposite math operation. All right, and we end up with 2x equals 6. All right, now we still want to get this x by itself, which means we have to get rid of the 2 as well. And by get rid of, I just mean move it over. But here we have 2 multiplied by x. And so to move that 2 over, we need to do the opposite math operation. So we're going to divide by 2 on both sides, because whatever you do on one side, you have to do on the other side. And you see how like doing the opposite math operation here cancels that out. By doing 2 divided by 2, well, that's 1. So cancels out. That's now what we're left with is our x value. Okay. So we're going to talk through a few examples that are on your next slides. Solving for different variables in each case. So for the first one, they give us the equation P1 V1 equals P2 V2, and they ask us to solve for P1. You see a lot of equations like this in chemistry where you have numbers represented as letters, okay? In an equation like this one, this is from our gas chapter that we'll cover later on. The capital P is pressure and the capital V is volume. So what the equation is really saying is that the pressure of gas 1 times the volume of gas 1 is going to be equal to the pressure of gas 2 times the volume of gas 2. And you don't need to have the numerical values to set your equation up, right? We can say, all right, if I want to get pressure 1 by itself, if I want to solve the equation for pressure 1, then I'm just going to divide both sides by the volume, okay? So if I divide my left side by V1 and my right side by V1, then V1 over V1, it cancels out because it's just equal to 1. And then what I'm left with is going to be P1 equals P2 times V2 over V1. Okay. And now if I actually had numbers for these, for pressure V2 and V1, I can plug those in and I can solve for P1. All right. I want to add in one more equation here to solve for because we did it in class. So let's say I have a different one of our gas laws from our later chapter. P1 over T1 equals P2 over T2. And let's say for this one, I want to solve for T2. Okay. If you want to solve for one of the variables that is in the denominator of a fraction, before you can isolate the variable and get it on one side by itself, before you can do that, you have to get it out of the denominator spot. Okay. The unknown variable that you're solving for can never be on the bottom of a fraction bar. It has to be up top. And so you have to go through the process of getting it into the numerator spot before you can isolate it. All right. So if you want to get the T2, the temperature value, temperature 2, into a numerator spot, the easiest thing to do is to multiply both sides by T2, right? Because over here, this will cancel out and turn into 1. And now on this side, if I multiply by T2 over 1, just look at what you're left with now. It's going to be T2 times P1 divided by T1. But now let me just write that so it looks more like it's in the same. There we go. But now my unknown, what I'm trying to focus on here, let's remind ourselves up here that we're trying to find T2. Now this T2 value is in the numerator position. So now I can work on isolating it and moving these things to the other side. Okay. And when you want to move these variables to the other side, for each of them, you just want to make sure you're doing the opposite math function to what's happening on the side that they originate on. So here, T2 is being multiplied by P1. So to move it over, I'm going to divide both sides by P1. And if you want to, another way that you can write out division is you can multiply by that fraction, right? So I can multiply and put P1 on the bottom here. And now you see like they're on opposite sides of the fraction bar, so they're going to cancel out. T1 in this case, which I also want to move over, this is getting divided on the left side. So to move it over, I'd have to multiply. So I can multiply by putting it on the top of that fraction bar. And now these are on opposite sides, so they cancel out. And because I'm multiplying my left side by T1 over P1, I have to multiply my right side by T1 over P1. And what you're left with at the end of that is going to be T2 all by itself because we canceled out everything else. And we have P2 times T1 over P1. Okay. And now if I had the two pressure numbers and the temperature number, I could figure out what my other temperature was. All right. Okay. So let's look at the study check 1.6. Those are some other equations that we're definitely going to see. So this, the question here is solve each of the equations for M, which is mass. All right, and our first equation is our heat equation, which we'll see in chapter 3. And then this is our density equation. And it's fine in equations when you have words or variables here. You just treat them like, I don't know, like just like letters if you want, or like it doesn't really matter what they mean if you are just trying to move them to the other side. It does matter what they mean once you actually are trying to solve them for a purpose, because you do have to know what all the different parts of the equation are once we get to chapter 3. But right now, when you're looking at this and none of this has any meaning to you, you can still solve the equation for the variable that you're interested in, just by recognizing that whatever this is and whatever this is, they're all being multiplied by each other. So if I want to isolate my mass value and solve my equation for my mass value, then I'll divide both sides by these two things. Right? Because if I divide my right side by both of these, it turns into 1. And if I divide my other side by them, then I've isolated my mass value. And what I'm left with is heat divided by my temperature change, which is what delta T stands for, times specific heat, which is what SH stands for. That's going to give me the mass of my substance, which is what M stands for. Okay. For our D equals M over V equation, this over. If I want to solve this one for mass, I see that my volume is in the denominator spot, so I'm going to multiply both sides by volume. I just like to put in the V over 1 so that you can picture that they're on opposite sides of the fraction bar. even if you put it on over 1 here, whenever you have a whole number, it's always over 1. So you can rewrite this equation now as volume times density equals mass. Okay. I'd like to add in one more here. Like if we're solving that D equals M over V equation again, but we solve it for volume instead. Because this is another example where we have our unknown in the denominator position. And again, the first thing that you want to do when you're approaching something, a calculation with an unknown in the denominator position, is move it into the numerator spot. So here we have to multiply both sides by volume. So basically we're doing this calculation again first as our first step, because we have to get that volume out of the denominator spot. But once it's out of the denominator spot and we have the equation looking like this, now we can isolate the volume by doing some division. And what we're left with is that volume equals mass over density. Okay. All right. We're going to look at some graphs next. It's the last of the key math skills for this chapter, I think, that we have to focus on. So let's go back to the slides. So when we have graphs, what we're looking at are relationships between two specific variables. Every graph is going to have two perpendicular axes, meaning that they're going to kind of form an L shape compared to one another. The horizontal axis is going to be the x-axis. The vertical axis is going to be the y-axis. Okay. So this is a visualization of a graph. The graph has, this is our vertical axis here. So y-axis is vertical. This is our x-axis, our horizontal one. And you'll notice that the graph has a title telling us what properties are being related to one another. And those properties are also labeled on the axis that they correspond to. Okay. So when we look at our y-axis in this graph, we know that all of these numbers represent the volume values that are in liters. And when we look at our x-axis here, we know that these numbers represent the temperature in degrees Celsius. Okay. Right. All right. And then the one other thing that the graph is going to show us, we can look at this. Each point on that graph represents the volume of a gas in liters that was measured at a specific temperature. So that means that like you can look at any point here and you can say, all right, at 30 degrees Celsius, the volume was measured and it was like, I don't know, a little less than 25 liters. Okay. You can go to 60 degrees Celsius. You see that where it intersects there and trace it back over here. And you're like, all right, well, at 60 degrees Celsius, the volume of the bloom was a little more than 27 liters. When you have a relationship like this one that's being represented in this particular graph, where both values increase with each other, that shows what's called a direct relationship. Okay, so that's telling us that as the temperature keeps increasing, the volume keeps increasing along with it. Right? But we can use the different graphs that we're given to help us answer questions. And we want to be able to interpret graphs like this one and answer the questions like the ones that are up on the slides now. So we have a different graph that we're looking at here. This is a graph of body temperature versus the time after Tylenol was administered to a patient. Okay. So on our vertical axis, our y-axis, this is going to be the body temperature in Celsius. The range of values on the vertical axis is going to go from 37 degrees Celsius, which is normal body temperature, up to 39.4 degrees Celsius, which is the spike of the fever in that case. On our horizontal axis, this is going to measure the time in minutes specifically after Tylenol was given. And our range of values here is going to go from 0 minutes, which is before we gave any Tylenol, up to 30 minutes. All right. So looking at the graph to answer some of these questions, what was the child's temperature after 15 minutes after Tylenol was given? So to answer this question, we're going to find the 15-minute mark on our graph, and we're going to see where it intersects our red line, or our curved line in this case. That's fine. And we're going to trace it back over to the spot where it intersects our vertical axis, and then give our best estimation of what that temperature would be, right? So if this is 37.4, this is 37.8, this would probably be 37.6, and maybe at 15 minutes, maybe we're a little bit below 37.6, but it'll be pretty close to 37.6, maybe 37.55 or something like that. All right. How many minutes elapsed for the temperature to decrease from 39.4 degrees Celsius to 38 degrees Celsius? So if we start at 39.4 and we go down to 38, 38 is going to be like right between these two marks. Okay. So we're going to trace over and we're going to see, where does this spot intersect our red line? It intersects it like right here, which is right between the 5 and the 10. So maybe like 7 minutes. That would be a pretty good estimation for that. It took 7 minutes for the temperature to decrease to 38 degrees Celsius. Another question, what was the decrease in degrees Celsius between 5 minutes and 20 minutes? Okay, so for this one, we'd have to look and say, all right, well, at 5 minutes, the temperature is about, let's say, we'll just say 38.4 to make it easier to read. We'll say it's almost halfway between those two values. So maybe at 5 minutes, our temperature is 38.4 degrees. And then at 20 minutes, the temperature is down to 37.4 degrees. So the difference, the decrease in degrees Celsius would be us subtracting those. And we're going to see a 1 degree difference. Okay. So hopefully that makes sense. The next thing we're going to look at is scientific notation. Scientific notation is a way that we're going to be able to look at really large and really small numbers and make it easier for us to work with them. Okay. Scientific notation is used when there's a lot of zeros that are in our values, because zeros can get confusing to work with. It's hard, sometimes you miss one. And missing a zero in a number leads to a pretty big difference in the value of that number. So you see scientific notation most often when you're working with numbers that are very, very large or very, very small. There's two parts to any number that's in scientific notation. There's going to be the first term, which is your coefficient term. And then there's going to be your second term, which is your power of 10 or your exponential term. Okay. And that's always going to be written as 10 raised to some exponent. The first term, your coefficient term, is always going to be expressed as a number between 1 and 10. And I'll show you why that's true when we look at the examples. And then that second term will always be the exponent term. And what you can keep in mind when you're doing scientific notation is that whenever you take the first term and you multiply it by the second term, you're going to end up with the value that you were originally starting with. Okay. Anytime that you're doing scientific notation and you want to use that as a last check for yourself, that would be a good idea to do. Because when you multiply your first term and your second term, you should always end up with what you started with. So let's look at these examples. I'm going to show you these two slides, and I'm going to work on the board for a little bit to go through some of the examples. But what I want you to keep in mind as we're doing this is that with scientific notation, we're going to be counting the numbers from we're going to be counting the places that we have to move our decimal to get it from wherever it was at the beginning until it's between our first two non-zero numbers. Okay. We'll keep track of how many places we move that decimal, because the number of places we move that decimal is going to become our exponent. And our exponent is going to be a positive value when the number that we start with is bigger than 1. And our exponent is going to be a negative value when the number that we start with is smaller than 1. Okay? But the process for both of these isn't going to change, because for both types of values, whether it's bigger than 1 or smaller than 1, our goal is always going to be to take that decimal wherever it is and to move it so it's between our first two non-zero numbers. Okay? So I'm going to work through the examples that are here on the board, and then I'm going to work through the other ones that are in our slides. So starting off with the number 17,413. When you're looking at this number, there is no decimal place in the number. And in any number that does not have a decimal place, you'll always assume that the decimal place would exist after the ones place. Okay, so we can assume that our decimal would be here if it was written. And our goal is going to be to move that decimal so it's back between our first two non-zero numbers. And we want to count the places that we're moving it. Okay, so 1, 2, 3, 4 places. It took us 4 jumps to get there. Okay, and so when we rewrite this number, it's going to be 1.7413. We don't change anything about those numbers. We're just putting our decimal here. And then our second term, our exponent term, is going to be times 10. And it's raised to the number of places that we had to move that decimal. Okay. In that second example, 174.13. Our decimal starts a little bit closer to where we need to move it to. All that means is that when we move that decimal over, it only has to jump 2 places, right? So now when we write that out, it's going to be 1.7413. I don't change anything else about the rest of that number. These terms look exactly the same, because when that decimal is between the 1 and the 7, all the other numbers that follow are still the same numbers. What's different between these two numbers is that I only moved this decimal 2 places, right? And if I put this in my calculator, what I would get back out is 17,413. If I put this in my calculator, what I get back out would be 174.13. Okay. Now for our numbers that are smaller than 1, that start out less than 1, we're going to be moving the decimal place in a different direction, right? We moved our decimal place in these first examples from the right to the left. In our numbers that are starting out as less than 1, we're going to be moving our decimal place from the left side to the right side. And that difference in direction is what's going to kind of signal to us that we're going to need to change the sign of our exponent. So when our numbers start out and they're less than 1, we still want to move that decimal so it's between the first two non-zero numbers. But when we go to write out our value, so in this case, it's going to be 1.74, times 10, I only moved it one place, but because the number was less than 1, my exponent's going to be a negative 1. Okay. And for that second example, 0.0000174. I take that decimal and I'm going to still count 1, 2, 3, 4, 5 places to get it between the 1 and the 7. 1.74 times 10 to the negative 5. Negative because the number I started with is smaller than 1. And you could still go back and double check this in your calculator, because if you put this in your calculator, it's going to give you back 0.174. If you put this into your calculator, it's going to give you back 0.0000174. Okay. So we have a few more examples that we want to try. If we go to the learning check, I skipped a couple of the slides because they're just examples. And well, actually, let me put this up real quick just to talk about this. This particular slide, it won't make much sense to you until you have your scientific calculator. But when you're actually keying scientific notation into your calculator, there's 2 keys on your calculator that you might see. It's either going to be an EXP for exponent or an EE key. And both of those things are ways that you can write in times 10. So if you have a calculator with either of these keys and you wanted to write 4 times 10 to the positive 6, you plug in 4, hit your EE key, and then you just have to write in the exponent. And a lot of times it'll display like one of these things on your calculator. If you need to put in a negative exponent, then you just do whatever the first number is, then you hit your EE key, and then you have to hit the positive negative sign and then the value, right? And then it still will show up the same way. But that E, sorry, my voice cracked, that E, that is representing that scientific notation. Okay. All right, so we're going to look at these 2 next, and we're just going to look at some of the other problems. Just want to make sure that we're on the same page with this. So it's asking us to write each of the following in scientific notation. Gives us 64,000 to start with. And then it gives us 0.021. Okay, so the first thing that you can assess is my number bigger or smaller than 1? Because that'll help you figure out whether your exponent should be positive or negative. Here, our number is definitely bigger than 1, so our exponent's going to be positive. Here, our number is smaller than 1, so our exponent's going to be negative. And now we're going to go to where this is a comma, just to be clear, 64,000. So we're going to go where our decimal place is assumed at the end of the number, and we're going to count back so it gets between the first 2 non-zero digits. So 1, 2, 3, 4. So it's going to go between the 6 and the 4. You don't have to include these particular zeros at the end. There's a reason for that when we get to significant figures. We can talk about it again. So we'll do the 6.4 times 10, and then the places that we jumped. So 1, 2, 3, 4. Positive 4 because our number started bigger than 1. For our second example, we start here and we're going to go 1, 2 places to get it between the 2 and the 1. And when we write out our exponent term, we're going to make sure to include the negative sign for the exponent, 10 to the negative 2. Okay. And the last 2 examples that we have for the next sample problem, they give us 3,500 and 0.00016. Okay, so again, I look at that number and I say it's bigger than 1, so I know that my exponent's going to be positive. And so now we're going to go to where the implied decimal is, count backwards, 1, 2, 3 places. So we end up with 3.5 times 10 to the positive 3. And then here we have a number that's smaller than 1, so we know it's going to be negative. 1, 2, 3, 4, 5 places that we moved it. 1.6 times 10 to the minus 5. Okay. All right, that's our scientific notation. So that's it for chapter 1. When we come back with a chapter 2 video, that'll have a little bit more of like the significant figures, the significant figure calculations, and some of the rounding stuff that we need to do. And this scientific notation stuff will tie in directly with that stuff as well. Okay.